Okay, so today we're going to talk about carboxylic acids, and they have the functional group COOH. It's usually written like this. So we've got a C double bonded to an O and another OH down here, and this is what gives the molecule its chemistry. So this is what determines how it reacts and what it reacts with. You name them by adding oic acid onto the end of your carbon skeleton. So if you have, say, 3 carbon atoms in your carboxylic acid chain, you would call it propanoic acid. And then if you've got any other bits on your carbon chain, you would just add that like you would any other compounds. So if you had a methyl atom on carbon number 2, you would say 2-methyl propanoic acid, and the bit with the carboxylic acid group on is always carbon atom number 1, just like it is in an aldehyde. So if you had the carboxylic acid bit on the end, you just count up the carbon chain to where the other groups are. Okay, so let's have a little go. Here is your basic carboxylic acid. So you've got your 4 basic carboxylic acids: methanoic acid, ethanoic acid, propanoic acid, and butanoic acid. If you want to make a carboxylic acid, you can make it from a primary alcohol, so you can oxidize it with the usual potassium dichromate and sulfuric acid. It has to be primary alcohol because obviously secondary alcohol would make a ketone and then wouldn't be able to be oxidized anymore. Just like that. So there's your primary alcohol, and you're oxidizing it into your carboxylic acid. You need to heat it under reflux, and there's your reagents: potassium dichromate and sulfuric acid. Physical properties of carboxylic acids, well, as you would expect, they can form hydrogen bonds because of the functional group on the end with the OH in, and this means they've got a higher melting point than you would expect for similar sized molecules with the same number of electrons. And they're able to mix quite freely with water due to the hydrogen bonds. Depends how big the carboxylic acid is. So you've got a particularly big carboxylic acid with a massive carbon chain, that probably wouldn't be able to mix as well as a smaller one due to a bigger hydrophobic area. Okay, so obviously carboxylic acids are acids. People usually forget that. They all ionize in water, which means that the H plus falls off the end to leave you with something that looks a little bit like this. So you've got your carboxylic acid here, and you've got an O minus where you did have a H here. So this is the bit that was the OH in the original carboxylic acid, and you will see this quite a lot with a carboxylic acid with a H plus missing, particularly if the carboxylic acid's in some kind of alkaline conditions. You can turn that back to your carboxylic acid really easily by just adding any acid you like, and it'll add a H plus on the end here. Okay, so carboxylic acids behave like acids, so they can release a hydrogen ion to make it acidic. That forms, you can just call it H plus, or the better way to call it is H3O plus, which is the H plus joined to a water molecule. And they react just like acid. You would expect acids to do so. Okay, so usual reactions of acids, like acid plus alkali, acid plus metal, that kind of thing, are all still there. Okay, so let's have a look at a couple of these reactions. So if we react carboxylic acid with an alkali, you've got your carboxylic acid here, so this would be ethanoic acid because it's got 2 carbon atoms, plus your alkali, sodium hydroxide, goes to the ethanoate ion here, so what you call the carboxylic acid without the H plus on the end, joined to an Na plus, so this is an ionic interaction between the Na plus and the CH3COO minus, and some water here. You could just write this like that because the Na plus is effectively a spectator ion. So it's fine. So you've got your ethanoate ion again with your water here. And this is often called the ethanoate ion. So you'll see lots of these. If you started with methanoic acid, you'd get methanoate ion. So it's basically carboxylic acid without the H plus on the end. Okay, if you reacted it with a base, you've got, again, your ethanoic acid, here's your base. This time you've got to balance your salt. So here's your salt, you've got Cu2+, so you need 2 of your ethanoate ion, just like when you do normal valencies. You need to make sure that you've got the right number of everything. So you've got 2 of those because this is 2+ ion. Again, we could just write that like that, because copper is effectively just spectating. Reaction with a metal, so again, typical reaction of an acid. You've got plus magnesium, you've got the ethanoate ion again, bonded to the magnesium as well there. Reaction with carbonate, so again, similar to other acids, you've got carbonate here from calcium carbonate or sodium carbonate that they wanted to react it with, producing a salt, CO2 and water. Or you could include the metal and write it like that. Okay, proton donor is basically what we mean by an acid. So this is what Bronsted and Lowry, two independent scientists, came up with as a theory of what is an acid. So acids can take off the H+ and give it to something else, and that's why we call them a proton donor. So in a lot of reactions, water is a proton acceptor, so that's accepting the base. So in this sort of reaction, your carboxylic acid is given away this H+, and the H+ has gone onto the water to make H3O+. And the carboxylic acid is quite good at doing this because of the functional group, because it's got 2 oxygens in this functional group. It means that the negative charge that you get can actually be delocalized over the whole functional group, over both of the oxygens, and this makes it quite stable because oxygen is quite electronegative. It's quite good holding on to that negative charge, and it'd be very stable if it's across 2 oxygens rather than just 1. So that makes it quite good at donating its proton and still having that negative charge stable. So just like this, you can change from the negative charge being on this oxygen to the negative charge being on this oxygen. I'll spend some time on each. Okay, new reaction. So this is not to do with it being a normal acid. It can form something called an ester. So it's when you get a carboxylic acid and an alcohol reacting together in the presence of an acid catalyst. So you've got your carboxylic acid here, the alcohol here. So your alcohol goes on to the carboxylic acid where the hydrogen was. So where the hydrogen in this functional group was, you swap it for whatever group is on the alcohol. Okay, if you want to name an ester, you've got 2 bits. You've got this bit, which came from the carboxylic acid, and you've got this bit which came from the alcohol. So you name this bit as according to what carboxylic acid it came from. So if it was ethanoic acid, it would be ethanoate, and the other bit with the alcohol. So let's have a look. So you've got the alcohol bit is the first bit, the carboxylic acid bit is the second bit. So the one on the previous page had an ethyl bit from the alcohol and the ethanoate bit from the ethanoic acid. Esters, you might know, are used as solvents and flavourings and things like that. They're usually quite smelly, so they're used as anything that needs a perfume or a flavour. Here's some examples of some esters. So just to illustrate the naming, see this one here, ethyl methanoate. It's got the ethyl bit here from the alcohol, and then it's got 1 carbon atom in the carboxylic acid bit, so that's where the methanoate comes from. Okay, hydrolysis of esters is basically breaking the ester back up into the carboxylic acid and the alcohol. So that's what hydrolysis means. You can have ester hydrolysis in the presence of acids or alkalis, and all it means is here's your ester, so this one would be ethyl ethanoate plus your water, heat it under reflux, and it's going to break back up into ethanoic acid and ethanol. If you do this in alkaline condition, so if you did it with an alkali rather than acid, you get what we talked about before, you would get the O- on the end of your carboxylic acid rather than the actual carboxylic acid itself. So you'd get the COO-. Acid hydrolysis is reversible and alkaline hydrolysis is not. So if you did it in alkali, you would get this rather than the carboxylic acid with the H here.